Welcome students. We are back with another lesson. In this lesson we'll discuss isotopes, isotones and isobars. Okay. Isotopes are isotones and isobars are nothing but a different configuration of the nucleus of the atom. So how we can categorize the nucleus of the atom? So nucleus can be categorized into three categories, which are your isotopes, isotones, isobars. So in this class we will study what are isotopes, isobars and isotones, and we will use a suitable example to explain them. So the first one is your isotopes. What are isotopes? The atom of an element which have same atomic number but different mass number are called isotopes. So all those atoms which have the same atomic number but different mass number. Okay, so for example you can take hydrogen, deuterium, tritium. In this case you have a hydrogen atom. Now inside the hydrogen atom, look how many protons are there? 1. Now let us take the second case, deuterium. Inside the nucleus, how many elements, nucleons are there? There are 2 nucleons. One is proton, the other one is your neutron. Next, look at your tritium. In the tritium, inside the nucleus, how many nucleons are there? 3. What are those 3 nucleons? One is proton and the 2 neutrons. Fine. So in all the cases, look at their atomic number. What does the atomic number means? The number of the proton inside the nucleus. So how many protons are here? 1. How many protons are here in deuterium? 1. How many protons inside tritium? 1. So in all the 3 elements, the atomic number is 1. Clear? Now, let's look at the mass number. The mass number means the total number of nucleons inside the nucleus. So in our first case, for the hydrogen, how many nucleons are there? 1, which is a proton. So the mass number is 1. Now look at your second case. In the second case, what is the mass number? The total number of nucleons? 2. One is proton, the other one is neutron. So the mass number is 2. Now look at your third case. In this case, what is the mass number? How many nucleons are there? 3. 1 proton and 2 neutrons. So in this case, the mass number is 3. So if you consider these 3 examples, the 3 elements have the same number of protons. That means they have the same atomic number, but the total number of nucleons are different. That means they have a different mass number. Fine. So such elements are known as your isotopes. Elements which have the same atomic number but different mass number. Now next, let's discuss isobars. The atoms of an element which have the same mass number but different atomic number are called isobars. So let's take the example. This is your argon, this is your potassium, this is your calcium. Now in case of your argon, look here, how many protons are there? 18 protons. In case of your, so look in the first case, the argon has 18 protons. In your second case, the potassium has 19 protons. In your third case, calcium has 20 protons. So in the 3 cases, are the different elements having the same number of protons? No. So if they don't have the same number of protons, that means they have a different atomic number. Fine. Next, now look at the number of nucleons. Inside the argon, there are 18 protons and 22 nucleons. So if you add 18 plus 22, you will get 40. So how many nucleons are there inside argon? 40. So what is the mass number of argon? 40. Similarly, Look at your potassium. The potassium has 19 protons and 21 neutrons. So in total, how many nucleons are there? 19 plus 21 is again 40. So inside the potassium, the mass number is also 40. Fine. Now look at your calcium. The calcium has 20 protons and it has 20 neutrons. So again, how many nucleons are there? 20 plus 20, which is 40. So inside calcium, you have how many nucleons? You have 40 nucleons. So its mass number is also 40. So in all these three elements, if you look, argon, potassium, calcium, are the mass number same? Yes. So elements which have the same mass number but different atomic number, such elements are known as your isobars. The next one is your isotones. The atoms of an element which have the same number of neutrons are known as your isotones. So let's take an example. Suppose you take oxygen. The oxygen's atomic number is 8. That means the proton number is 8. The mass number is 16. That means how many neutrons will be there? So if the oxygen has atomic number 8, mass number 16, then the number of neutron is given as A minus Z. That means 16 minus 8, which is 8. So the number of neutrons inside the oxygen atom is how much? 8. Fine. Now similarly, let's take the nitrogen. The nitrogen's atomic number is 7. Mass number is 15. Then how many neutrons will be there? It will be 15 minus 7, which is 8. So how many neutrons are there inside the neutron? How many neutrons are there inside nitrogen? 8 neutrons. Fine. Now let's take another example. Carbon. The carbon's atomic number is 6. Mass number is 14. So in this case, how many neutrons will be there? 14 minus 7, which is also 8. So in all these three cases, look at the number of neutrons. Oxygen has 8 neutrons, nitrogen also has 8 neutrons, carbon also has 8 neutrons. So if different elements have the same number of neutrons, the nuclei of such atoms or such elements are known as your isotone. Fine. So let's just do a quick revision. If the atom has the same atomic number, such elements are known as isotopes. If the atoms have the same mass number, such elements are known as your isobars. And finally, if the atoms have the same number of neutrons, such elements are known as isotones. Fine. So these are your isotopes, isobars, and your isotones. Now next we'll discuss or we'll write down the values for 1 AMU. Okay. So what does 1 AMU means? So let's take an example of carbon. Why carbon? Because it is most abundantly found atom in the nature. Okay. It is the mostly found atom in the nature. Now if you take a carbon atom, fine, and if you measure the carbon atom, it weighs somewhere around 1.992678 times 10 to the power minus 26 kg. This is the one weight of carbon atom. Fine. Now inside this carbon atom, let's forget about the mass of the electrons. Okay, the electrons are very light. Okay, so we can ignore the mass of the electrons. So now let's consider this carbon atom. So let us suppose this carbon atom, inside this carbon atom, how many inside the nucleus of the carbon atom, how many nucleons will be there? There are 12 nucleons inside the carbon atom. So if you take a closer look inside the carbon atom, okay, the carbon atom has 1, 2, 3, 4, 5, 6 proton. So its atomic number is 6. Apart from this, the total number of nucleons inside the nucleus of the carbon atom. Okay, count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 nucleons inside the carbon atom. So its mass number is 12. So I can write this one as 12C6. Fine. This is your mass number. This is your atomic number. So inside the nucleus of this carbon atom, there are 12 nucleons. And this carbon atom weighs 1.99 times 2678 times 10 to the power minus 26 kg. So if I ask you what will be the mass of individual nucleons, what you will do? Okay, consider the fact that the protons and neutrons, okay, they are almost equal mass. Okay, approximately they have the same mass. Fine. So instead of considering proton and neutron as a different particle, just consider them as the same particle having the same mass for now. Okay, so consider there are 12 particles having the same mass and the total mass is this much. So if I ask you what will be the mass of the individual nucleon, then what we have to do? We have to divide this total mass by the number of the nucleons. And in this case, how many nucleons are there? 12. So if I divide this one by 12, I will get 1.66 times 10 to the power minus 27. Fine. So 1 atomic mass per unit means the mass of the individual nucleons. No matter whatever atom be, whether it be carbon or any other element, okay. Here, the mass of the individual nucleons, whether it be neutron or proton, will be somewhere approximately, okay. I'm not saying exactly it will be 1.66, but it will be approximately 1.66 times 10 to the power minus 27. Fine. So this unit gives us 1 atomic unit. So 1 atomic unit is 1.66 times 10 to the power minus 27 kg. Fine. So this is your 1 AMU. You can remember this 1 AMU. Okay. I'll tell you why this 1 AMU is important. This 1 AMU is important because in your nuclear physics and your atomic physics, okay, whatever mass we will consider, whatever mass we will write, we won't write in terms of kg. We will write in terms of AMU. Why is it so? Because if you see, it is whatever be the particle, it will be of the order of 10 to the power minus 27. Okay, and this is a very small quantity. Apart from this, it is not feasible or it is not handy when you are doing calculation. So whenever we write any mass in your nuclear or your atomic physics or in your chemistry, we will mostly use 1 AMU. Fine. So suppose if I want to show example. So suppose you have a mass of an electron. The electron mass is 9.11 times 10 to the power minus 31 kg. Okay. So look at the order minus 31. Okay. So what I can do is instead of writing it in terms of 10 to the power minus 31 kg, I can simply substitute this mass from the AMU. Okay. To convert this kg into AMU, what you will do is you will divide this quantity by 1.66 times 10 to the power minus 27. Okay, so if I divide 9.11 times 10 to the power minus 31 kg by 1.66 times 10 to the power minus 27 kg, I will get 0.00055 AMU. Clear? So the mass of electrons in terms of AMU can be written as 0.00055 AMU. Okay. Similarly, if I want to express my proton, so my proton weight is 1.6726 times 10 to the power minus 26 kg. So if I want to express it in terms of AMU, I can write down. First, what I have to do, I have to divide this quantity 1.6726 times 10 to the power minus 27 kg by 1.66 times 10 to the power minus 27 kg. And if you divide, you will get 1.0073. So the mass of proton, if I want to express in terms of AMU, I can write as 1.0073 AMU. Can you see? The mass is almost equivalent to 1 AMU. the difference is in that somewhere around 10 to the power minus 3, 10 to the power minus 4. This is very small difference. Okay, we can ignore this difference. So the mass of protons in AMU can be expressed in this numbers. Fine. Similarly, if I want to express my neutron, so if I want to express my neutrons weighs 1.6749 times 10 to the power minus 27 kg. And if I express it in terms of AMU, I can write it as 1.0086 AMU. Now, if you compare the mass in the AMU, look, both of them are very close to the 1. The only difference is in the 10 to the power minus 3 and 10 to the power minus 4, which is very negligible. So that's why I've said the proton and the neutron are almost equivalent mass. Clear? So why we need this AMU? So that we can express the mass of the protons, the mass of the neutrons, the mass of the electrons, which are very small quantities, in terms of AMU. Okay, this will be helpful when we'll solve some numericals. The next one is your 1 electron volt. 1 electron volt means how much energy or how much potential difference or how much energy is required by this electron to accelerate in a potential difference of 1 volts. Okay, this quantity I've already discussed in my chapter 11, dual nature of radiation and matter. There I have already calculated its value. The value of 1 electron volt is 1.602 times 10 to the power minus 19 joule. So whenever your energy will be given in this order, 10 to the power minus 19, and the unit will be joule, what we will do is we will convert it into electron volts. Fine. So this too will help us during the numericals. Okay, for now you can just remember the values, only these values. Okay, and if you want to further remember, you can remember the mass of the electrons, 0.00055. Remember the mass of the proton, you can remember up till this value 1.0073 AMU. Mass of the neutron 1.0086 AMU. Okay, so this will help us when we solve the numericals. Okay, so that's it for today's class. Thank you, and if you have any confusion, please feel free to ask. I will re-explain to you again. So again, thank you.